I want you to imagine a pretty baffling medical scenario for a second. You have this perfectly healthy baby boy.
Okay.
He is bouncing, smiling, hitting all his developmental milestones without, a single issue.
Right, doing great.
But then, almost like a biological clock strikes midnight, on the exact day he turns 6 months old, a switch just flips inside his body.
Yeah, wow.
Yeah. Suddenly, he starts suffering from recurrent, severe respiratory infections. We're talking otitis media, bacterial pneumonia, just one right after the other.
That is a terrifying situation for any parent.
Exactly. He goes from robust, perfect health to severe vulnerability, literally overnight, at exactly half a year old.
But, for a diagnostician, that 6-month mark is a massive, glaring clue.
It's not a coincidence.
Not at all. It's not random. That timeline actually offers a very specific window into how our bodies learn to defend themselves and what happens when those defenses are stripped away.
And decoding those defense mechanisms is basically our mission for today. We are taking a deep dive into the fundamentals of the human immune system.
Right.
And we're using the foundational concepts from the medical syllabus, NMS Immunology, 3rd edition by Richard M. Hyde.
Classic.
It is. Our goal is to break down your body's ultimate defense network for you. We're going to explore the basic physical barriers, the incredibly complex cellular warfare happening in your bloodstream right this second.
Which is wild to think about.
It totally is. And then we're going to apply this science to real-world clinical vignettes, just like that mystery with the 6-month-old baby.
Yeah, because immunology can often feel like, an overwhelming alphabet soup of acronyms and cell types.
Oh, absolutely. So many letters.
Right. But if we focus on the underlying logic of how these cells operate, it's essentially the most sophisticated synergistic military operation on Earth.
Yeah.
So immunity is simply the sum of all naturally occurring defense mechanisms that protect us from infectious disease. And to understand it, we divide this military into 2 distinct but highly cooperative branches. You've got the innate system and the acquired system.
Let's unpack the innate system first.
Yeah.
This is your non-specific immunity.
Exactly.
Meaning this branch of the military doesn't really care what the invader is. It could be a cold virus, a staph bacterium, or just like a random speck of dust you inhaled.
Right. It doesn't matter.
It simply recognizes that the object does not belong in your body.
And that's the beauty of it. Innate immunity relies on inherent physiologic mechanisms. It's your first line of defense, and it is beautifully brutal in its simplicity.
Yeah.
We start with physical barriers. Intact skin is composed of a keratinized outer layer of dead cells.
Right. So unless it's physically cut or damaged, it's virtually impenetrable to most environmental organisms.
Exactly.
But obviously we have openings in our bodies. I mean, we have to breathe and eat.
Unfortunately for our immune system, yes.
Right. So the innate system relies on things like the mucus blanket, which sounds a bit unappealing.
A little gross, yeah.
But it's an incredible piece of engineering. You have these epithelial cells lining your respiratory tract that are coated in viscous mucus, and they possess these tiny hair-like structures called cilia.
And they are constantly beating upwards.
Constantly.
We actually call that the ciliary escalator.
I love that term.
It's very descriptive. If you inhale a fungal spore right now, it gets trapped in that sticky mucus. Those beating cilia physically sweep it upward, away from your vulnerable, sterile lungs.
So it can be coughed out or harmlessly swallowed.
Right. And if you do swallow it, it immediately faces chemical barriers. The incredibly low pH of your stomach acid basically dissolves most pathogens right on contact.
And it's not just stomach acid. I mean, if a microbe lands in your eye, your tears contain an enzyme called lysozyme.
Oh, yeah, lysozyme is gross.
It literally hydrolyzes it, breaks open, and dissolves the cell walls of certain bacteria.
It just melts them.
Yeah. The innate system even factors in broad systemic variables, like your body temperature, your oxygen tension, and your age.
That's a huge one.
Right. If you're an infant under 3 years old, or an adult over 75, your overall immune responsiveness is naturally suboptimal. The machinery is either still booting up or, slowly wearing down.
So we have a system that is always on and always deploying the same blunt instruments.
Right. It's like medieval castles' defenses. You have the moat, the thick stone walls,
The boiling oil.
Exactly. The boiling oil you dump on anyone trying to scale the wall. It's blunt, and it doesn't change its tactics based on who is attacking.
Right.
But castle walls aren't always enough. Pathogens evolve. They find really clever ways to breach those innate barriers.
Which is exactly why you need the second branch, right?
Yeah.
Specific or acquired immunity.
Acquired system.
Yes. This is a highly specialized, customized response that is induced only by exposure to a specific foreign agent, what we call an immunogen or an antigen.
Okay, so if the innate system is the castle wall, specific immunity is like an elite, highly trained bounty hunter.
I like that, a bounty hunter with a photographic memory. Specific immunity has three essential characteristics that separate it entirely from the innate system. First, the ability to distinguish self from foreignness.
Okay.
It knows your own tissue architecture and only targets outsiders. Second, extreme specificity. It doesn't just attack bacteria in general.
Right.
It attacks the exact, precise molecular structure of the specific strain it was trained to find. And third, immunologic memory.
That memory aspect is totally fascinating to me because it happens in two distinct phases. When you're first exposed to a new pathogen, you enter the induction phase.
Right.
The bounty hunter essentially has to study the target, learn its weaknesses, and build a custom weapon. That takes time.
Which is why you actually feel sick during a primary immune response.
Exactly. But if that exact same invader ever dares to show its face again...
You trigger the secondary or anamnestic response?
Anamnestic.
Right. Thanks to immunologic memory, your body has kept a silent reserve of sensitized cells circulating for years, sometimes decades. Yeah, so upon re-exposure, the response is overwhelmingly rapid and vastly more powerful. The invader is destroyed before you even register a single symptom.
And this specific branch is driven by lymphocytes. We have humoral immunity, driven by B cells that differentiate into plasma cells.
To secrete immunoglobulins.
Right, which are antibodies into the blood plasma. And then we have cell-mediated immunity, driven by T cells.
Which don't secrete antibodies.
Right, they don't. Instead, they engage in direct, hand-to-hand cellular combat and regulation.
And to truly appreciate how this combat works, we have to zoom down to the microscopic level.
Let's do it.
How does the immune system actually hunt and destroy pathogens once they breach those castle walls?
Right.
This brings us to the professional eaters of the immune system, the phagocytes.
The eaters.
Specifically macrophages and a type of white blood cell called neutrophils.
Actually, I want to pause on neutrophils for a second because you'll often see them referred to in medical literature as PMNs.
Yes.
That stands for polymorphonuclear leukocytes. It sounds completely terrifying.
It's a mouthful.
It really is. But it just refers to the strange, multi-lobed, almost alien shape of their nucleus.
Exactly.
And the way these PMNs and macrophages hunt plays out like a microscopic horror movie for bacteria.
Yeah, it really does.
It starts with a process called diapetesis. These white blood cells actually alter their own cytoskeleton to physically squeeze themselves through the tiny gaps in your capillary walls.
Just to get into your infected tissues.
Right.
They leave the bloodstream and enter the tissue because they are following a scent. This is chemotaxis.
Chemotaxis, okay.
Imagine the phagocyte following a chemical concentration gradient, basically a trail of molecular breadcrumbs.
Oh, I see.
Certain molecules act as powerful chemotaxins. These can be peptides shed by the bacteria itself, or a specific protein from your own immune system called C5a.
Right.
The phagocyte senses where the concentration of these chemicals is highest, and it crawls directly toward the site of infection.
So it tracks the target down using chemical sense,
Yeah.
and then comes the capture.
The fun part.
Right. The phagocyte physically makes contact with the bacteria, reaches out, and surrounds the particle with its own cell membrane. It just engulfs it entirely. The bacterium is now swallowed whole, trapped inside a little internal cellular bubble called a phagosome.
But, you know, swallowing the pathogen alive isn't enough. It has to be dismantled.
Right, you can't just leave it in there.
Exactly. Inside the phagocytic cell, there are these membrane-bound bags filled with highly toxic digestive enzymes.
Lysosomes.
Yes, lysosomes. The lysosome physically fuses with the phagosome bubble, creating a single sealed chamber of death called a phagolysosome.
A chamber of death.
And the weapons unleashed inside this chamber are formidable.
There are two main killing mechanisms here, right? Oxygen-independent and oxygen-dependent.
That's right.
The independent one uses tools we've already mentioned, like lysozyme to pop the bacterial wall, or basic peptides called defensins. But the oxygen-dependent mechanism is just wild. It relies on something called a respiratory burst.
Right.
The cell rapidly consumes oxygen to trigger a cascade of lethal, toxic oxygen metabolites. It produces superoxide anion, hydrogen peroxide, and eventually hypochlorite.
It basically manufactures lethal oxidants on demand.
Okay, wait, I have to stop and challenge the evolutionary logic of this.
Go for it.
A hydrogen peroxide, hypochlorite. Hypochlorite is literally the active ingredient in household bleach.
Yes. It is.
Are you telling me that right now my white blood cells are manufacturing bleach and peroxide inside their own bodies?
I hear him.
How is the risk of self-destruction not just, like, way too high? How do they not completely dissolve themselves from the inside out?
It is a profound engineering problem, honestly, and the solution lies in strict biological containment.
Okay.
An enzyme called myeloperoxidase facilitates the reaction, combining hydrogen peroxide with a halide ion, like chloride, to create that hypochlorite bleach.
Right.
But this incredibly toxic reaction is occurring strictly within the confined, heavily reinforced walls of the phagocytosome.
Oh.
The bleach is synthesized in an isolated, locked chamber where the bacteria is trapped. The rest of the host cell's delicate cytoplasm is completely protected.
Wow.
It's akin to detonating a bomb inside a heavily shielded internal disposal tank.
Unbelievable. So you have microscopic bleach factories roaming your blood.
Basically, yeah.
But they aren't the only assassins out there. We also have a completely different class of killer, right?
Yeah.
Natural killer cells, or NK cells.
Yes, NK cells.
And these guys operate on a totally different set of rules compared to the T cells.
That distinction is crucial. T cells are highly specific, but they are subject to something called major histocompatibility complex, or MHC, restriction.
MHT restriction.
Right. Think of the MHC as a molecular ID badge or a specific platter. A T cell can only recognize and attack a target if pieces of that target are formally presented to it on this very specific MHC platter by another cell.
But NK cells don't care about the ID badge. They don't need the platter.
Exactly.
Yeah.
NK cells bypass MHC restriction entirely. They provide a broad, immediate, innate surveillance system. They don't need prior exposure, and they don't rely on immunologic memory. Their primary job is to patrol the body and destroy virally infected autologous cells or tumor cells.
Autologous meaning your own body's cells that have gone rogue.
Right. As you're sitting there listening to this, you likely have NK cells silently destroying microscopic mutated cells in your own body before they can ever form a tumor.
That is just incredible. And their weapon of choice is just as terrifying as the bleach factories.
Oh, yeah.
NK cells use proteins called perforins. When an NK cell intimately contacts a rogue target cell, it releases these perforins. They physically insert themselves into the target cell membrane and polymerize. They link together to form an open channel. Essentially, they punch a massive gaping hole in the target cell.
And the physical integrity of the target is instantly compromised. Essential metabolites leak out, water rushes in due to osmotic pressure, and the tumor cell simply dies.
Wow.
And to your earlier point about preventing self-destruction.
All right, how do they survive that?
The NK cell's own membrane contains a specific protein literally named protectin.
Protectin. That's easy to remember.
Very on the nose. It binds to perforins to prevent the NK cell from accidentally punching holes in itself during the attack.
Amazing. So we have physical barriers, we have phagocytes dissolving things in bleach, we have NK cells punching holes in tumors. These are the cellular warriors.
They are.
But what happens when a bacteria is too slippery for a macrophage to grab? We need a long-range weapon.
Right.
That brings us to the humoral arsenal, the weapons floating freely in the fluid of your blood plasma, specifically the complement system.
The complement system is an absolute masterpiece of biological synergy.
Okay.
It's a group of at least 15 different proteins, primarily synthesized in your liver, that circulate in your bloodstream in an inactive, dormant state. But when they encounter a threat, they activate sequentially in a cascading manner. One protein cleaves and activates the next, which activates the next.
Like dominoes.
Exactly. This creates a massive amplification loop. A single trigger can activate thousands of complement proteins in milliseconds.
There are a couple of ways to start this domino effect, like the classical pathway, which involves an antibody binding to a target, or the alternative pathway, which just requires the physical presence of certain microbial surfaces.
Right.
But either way, they both lead to the same explosive finale, the membrane attack complex, or MSC.
Similar to the perforins used by NK cells, the late-stage complement proteins, specifically C5 through C9, assemble together on the bacterial membrane to build a physical pore.
Okay.
It punches a hole right through the bacterial cell wall, leading to rapid osmotic lysis. The bacteria simply bursts.
So the cascade built hole punchers. But that's not its only job. One of the most vital concepts in this entire deep dive is a mechanism called opsonization.
If we really want to understand how the innate and specific immune systems cooperate, opsonization is the key. Certain molecules act as opsonins. The two primary wares are IgG antibodies from the specific system and a split product of the complement cascade called C3b from the innate system.
Z3B, right.
These opsonins bind tightly to the outer surface of an invading bacteria.
I try to picture this like a culinary mechanism.
Oh.
Yeah, so many dangerous bacteria actually have these slimy, evasive outer capsules that make them incredibly hard for a macrophage or neutrophil to physically grip.
Right, very slick.
It's like trying to pick up a wet, heavily oiled rock with your bare hands.
Good luck with that.
Right. But when IgG antibodies and C3b proteins coat that bacteria, it's like slathering that slippery rock in a stung, highly appetizing glaze.
That is a very visual way to put it, but it's accurate. Your phagocytic cells actually possess specific membrane receptors, think of them as cellular taste buds, that are perfectly shaped to grab onto these opsonins.
Wow.
They have receptors that specifically lock onto the C3b protein and receptors that lock onto the tail end of the IgG antibody, which we call the Fc portion.
It's like the antibody provides a literal handle for the macrophage to grab.
Exactly.
The specific acquired immune system deploys the antibody, which triggers the innate complement cascade to coat the target in C3b, which exponentially increases the ability of the innate phagocyte to ingest and destroy it.
It bridges the gap entirely. The synergy is absolute.
It really is.
But the true test of understanding these mechanisms is seeing what happens when they break down.
Exactly. Let's frame the rest of our clinical rounds around a central theme. What happens when the immune system fails?
Okay.
It generally fails in three ways. It's either missing, it overreacts, or it attacks itself.
Right.
Let's start with missing. This brings us right back to the mystery we opened with. The 18-month-old boy with a history of recurrent cytopulmonary infections that began mysteriously at exactly 6 months of age.
Right. To solve this, we have to look at how specific immunity is acquired in early life.
Okay.
During pregnancy, a mother passes her own protective IgG antibodies directly across the placenta into the fetal bloodstream.
Oh, wow.
This is a form of naturally acquired passive immunity.
So the baby is basically born wearing his mother's immune armor.
Right, but it's a rented armor. IgG has a finite half-life. It naturally degrades over time.
Okay.
Statistically, that maternal antibody protection wanes and drops to critically low levels right around the 6th month of the infant's life.
So at 6 months, the mother's armor falls off.
Yes.
Normally, a baby's own immune system has booted up by then, synthesizing its own antibodies to replace the mother's. But in this boy's case, he had an underlying genetic immunodeficiency.
Perhaps an inability to synthesize his own immunoglobulins or, a genetic defect in his phagocytes.
Right.
The 6-month mark didn't cause his disease. It unmasked a severe vulnerability that was there all along, temporarily hidden by the maternal antibodies.
Wow.
Once that barred protection was gone, opportunistic bacteria that cause otitis media and pneumonia were free to attack unchecked.
It makes perfect sense when you understand the timeline.
It really does.
Now, what about when the system fails by overreacting, when it attacks something harmless? This is hypersensitivity.
Yes.
We have a clinical vignette of 2 Girl Scouts, Dana and Deb. They're walking through a meadow. Dana gets stung by a bee and almost immediately starts wheezing, her chest tightens, and she breaks out in a diffuse rash.
Dana is experiencing a immediate hypersensitivity reaction. This is anaphylaxis.
Right.
It's mediated by the IgE class of immunoglobulins. A prior hidden exposure to bee venom sensitized her.
Okay.
Her specific immune system mistakenly flagged the venom as a massive threat, causing her body to produce specific IgE antibodies.
I see.
These antibodies then attach themselves to the surface of mast cells and basophils in her tissues.
So her mast cells became like loaded springs.
Exactly.
When she got stung the second time, the venom antigen cross-linked those IgE antibodies on the mast cell surface. This caused the mast cells to instantly degranulate, dumping massive amounts of histamine and vasoactive compounds directly into her system.
And this results in severe local edema in the bronchioles, causing the wheezing and violent, smooth muscle contractions.
Which is life-threatening.
Very much so. The treatment here must be immediate. Epinephrine, which reverses the airway constriction and stabilizes those mast cell membranes.
But then you have her friend, Deb.
Right, Deb?
Deb didn't get stung, but she wandered through a dense patch of poison ivy. Now, Deb doesn't get sick right away. She seems fine. But a day or two later, she breaks out in an intensely itchy, blistering rash. Why the delay? And more importantly, why does the medical syllabus explicitly say we should discourage the use of oral antihistamines for DEB?
Because Deb is experiencing a completely different mechanism. She is having a type 5e hypersensitivity reaction.
Type 4.
Yes, this is a cell-mediated delayed reaction. It isn't driven by IgE antibodies, and it isn't driven by histamine.
Oh, interesting.
It is driven by sensitized T lymphocytes reacting to a specific chemical called urushiol found in the poison ivy sap.
So it takes time because the T cells actually have to physically migrate through the tissue to the site of the antigen and release their inflammatory mediators, which are called lymphokines.
Exactly. The delay is simply the biological time required for cellular migration and activation.
Right.
And because histamine is not the primary driver of this tissue damage, the T cell lymphokines are giving her an antihistamine won't address the root cause of the severe contact dermatitis.
You're targeting the wrong weapon.
Precisely. You need treatments that calm a cellular response, like topical corticosteroids.
It completely changes your approach to treatment just knowing which branch of the military you're dealing with.
It really does.
Finally, let's look at the third way the system fails, when it attacks itself.
The worst case scenario.
Yeah. The syllabus discusses a malignancy called multiple myeloma. This involves a patient presenting with deep, severe bone pain and hypercalcemia, dangerously high calcium levels in the blood.
Multiple myeloma is a devastating example of a plasma cell dyscrasia. A dyscrasia just means a disordered or abnormal state. We discussed earlier how B cells mature into plasma cells to act as antibody factories. In myeloma, a single mutant plasma cell becomes malignant.
Okay.
It goes rogue and begins to rapidly, uncontrollably multiply within the bone marrow.
And because it's a plasma cell, its entire biological purpose is manufacturing immunoglobulins.
Yeah.
So this infinitely multiplying cancerous clone just starts pumping out massive, excessive quantities of a single useless type of antibody.
We call this a monoclonal gammopathy. Mono meaning one, clonal meaning from a single cell.
Okay.
But these malignant cells are defective. Often they produce excess unattached light chains of the antibody molecule.
Light chains.
Yeah, and because these light chains are incredibly small proteins, they filter right through the kidneys and end up concentrated in the patient's urine.
Oh, wow.
Clinically, these are known as Bence-Jones proteins, which serve as a classic diagnostic marker for the disease.
But why the deep bone pain? Why is calcium spiking in the blood?
Well, you have to picture the bone marrow as a finite physical space, a factory floor. These malignant plasma cells are proliferating so densely within that limited marrow space that they physically crowd out normal cells.
I see.
In doing so, they secrete factors that stimulate osteoclasts, which literally dissolve the surrounding bone architecture.
They dissolve the bone?
They punch physical holes in the bone, known as osteolytic lesions. As the bone dissolves, all that stored calcium is released into the bloodstream, causing the hypercalcemia.
That is horrifying.
It's a stark mechanical reminder of what happens when the factory designed to protect you undergoes a malignant transformation.
It's sobering to realize that the machinery keeping us alive is so potent that a single rogue cell can dissolve bone.
It really is.
But understanding the precise mechanism, the why and the how, is the only way we can develop therapies to fight it.
Absolutely.
Okay, to wrap up our deep dive and reinforce this medical focus for you listening, I have a rapid-fire clinical challenge based directly on the mechanisms we just covered.
All right, let's hear it.
Based on everything we've discussed today, imagine you have a patient with a rare genetic defect that completely prevents their liver from forming the complement protein C3b.
Okay, no C3b.
What specific cellular eating process will be severely impaired, and what critical flavoring mechanism is lost?
Well, phagocytosis will be severely impaired.
Yeah.
Because without C3b, the patient loses the vital opsonization effect.
Right.
The body can no longer tag or glaze slippery bacteria, making it incredibly difficult for the neutrophils and macrophages to get a grip and ingest the invaders.
Nailed it. C3b provides the handle, and without it, the phagocytes go hungry and the patient gets sick.
It perfectly ties together the innate and acquired systems, and, it leaves us with a broader concept to consider.
What's that?
When you realize that your immune system is already capable of deploying localized bleach factories, assembling proteins to perforate cell membranes, and maintaining a customized molecular memory for decades, you have to wonder,
Wonder what?
how much of the future of modern medical intervention isn't about inventing new synthetic drugs to fight the battles for us, but rather learning how to gently steer, augment, and target the internal cellular army that has already spent millions of years perfecting the art of war.
That is definitely something to chew on.
Okay.
Until next time.